Hello everybody, I'm Sonu Mehta. I work as a research software engineer at Microsoft Research India. I work on a project called Sankey that uses data-driven techniques to improve DevOps pipeline in general. In today's talk, I'm going to talk about a tool called Rex that uses correlated change analysis to prevent misconfigurations. This is joint work with a bunch of other people in the lab. Let me start by describing a scenario. Alice is a new developer who has recently joined a team and she is asked to rename old microservice to new microservice. She goes ahead, makes changes in file registry_entry.xml. Along with this file, she is expected to make changes in 3 other related files: ITA load balancer, common load balancer, and firewall rules.xml. But as these things are not documented very well, she goes ahead and makes changes in 2 of the related files, but forgets making change in firewall rules.xml. Again, as these things are not caught by a compiler, the code change gets checked in and boom, it leads to service disruption because now the firewall rules are no longer mapped to the newly renamed microservice. In this case, as you saw, a small missing configuration change led to a huge outage or service disruption. And this is not a contrived example. We have taken this example from one of the Office 365 repositories of Microsoft. In fact, this problem is not really specific to one company. Various companies such as Facebook, Google, Amazon have faced outages because of misconfigurations. As these large-scale services become more configurable, outages or service disruptions because of misconfigurations have become a serious issue. And these outages have serious financial and security consequences. So all this motivated us to delve deeper into the issue of misconfigurations. The very first question that came into our mind is, why do we need configuration files at all? Based on our case study, we realized that large-scale services are very dynamic and agile. They have hundreds and thousands of knobs for various features to determine their behavior, for gating feature rollouts, running A/B testing experiments, updating machine learning models, etc. Every day, hundreds and thousands of config changes are made to these files, and all these changes have to be made without application redeployment or restart. So what I mean here is, if all these knobs or configuration parameters are made part of the code, and if we have to make 100 changes per day, then the application needs to be redeployed or restarted 100 times per day, which hampers the dynamism and agility of these services. So this justifies the presence of configuration files to some extent. But then the second question is, why is configuration management so difficult? Again, based on analysis, we realized that there are varieties of configuration files across different services, and the dependencies or correlations across these files emerge organically and is very different from one service to another. Unlike code, which has syntactic and semantic structure associated with it, configuration files lack that rich information, and so no compilers exist for configuration-related dependencies. Moreover, it's very hard to document all these correlations because they keep changing frequently. Just take a look at this plot. In this case, this shows basically the increase in number of XML files in the last 6 months. And as you can see, the number has simply doubled from about 3,000 to more than 8,000 in the last 6 months. Imagine how big the number would be if we include all types of configuration files and the correlations across them. So in general, configuration management is a difficult problem, and people have tried to deal with it in their own ways. We are not the first one, and there have been a lot of related work in this space. So this work at SOSP talks about holistic configuration management at Facebook, where they use config as a code approach for configuration management. But as part of this, the developers have to manually define the invariances for the configuration files, and this becomes a problem when they have to scale it to hundreds and thousands of configuration files. This work at ASPLOS 2014 talks about a tool called Encore for misconfiguration detection. This tool uses state-of-the-art association rule mining algorithms for learning correlations across files. But as these algorithms are not able to scale well with the increase in configuration files, developers have to manually define some templates to guide the learning process. And again, this becomes a problem when new files are added into the system. So all these techniques try to solve configuration management in some or the other way, but manual input becomes a challenge when they have to scale it to thousands of configuration files. We have tried to come up with a completely automated tool called Rex that uses correlated change analysis to detect these misconfigurations before they get manifested into the system. With the ubiquitous use of version control systems like Git, we have a lot of information available about the historical changes made in a particular PR, And we want to exploit that information to guide a learning process instead of asking developers for manual input. So this work has been accepted and presented at NSDI 2020, and I'll be talking about it in detail in the upcoming slides. As I said, REX is a correlated change analysis tool, and it's a two-step process. First is change rule discovery, followed by change rule refinement. Let me start by change rule discovery first. Change rule discovery is essentially a market basket analysis model where input to the system is a set of commits. A commit is nothing but a set of file changes made by the developer at one point of time. A set of such commits is input to a rule mining algorithm, which in our case is FP growth, and it outputs a certain set of rules that are basically the correlations across files. This work is inspired from Tom Zimmerman's work on mining version histories to guide software changes. This is how a typical rule looks like. So in this case, as you see, when file X was changed, which in this case is content filter spam we expect a change to be made in file Y, which in this case is post content filter spam Each rule has two additional hyperparameters called support and confidence. Support is basically the number of commits in which both file X and Y were changed together in the past. And a confidence value of 0.8 here means that out of 100 commits where file X was changed, in 80 commits, file Y was changed along with it. So we can consider REX as a rule learning engine that learns these correlated config changes, and now it can be used as a domain-specific compiler, as a suggestion engine, etc. Even as part of a suggestion engine, we can make suggestions to the developers when they're making changes in some files, but not making changes in the correlated files. And these suggestions can be made in the dev environment when the developers are making changes in a code editor, or they can be made in a pull request when the developers have already committed the changes. So currently REX is deployed as a suggestion engine that makes suggestions at pull request level, and it is enabled as part of Project Sankey, the bigger umbrella under which REX as a subtool. So we got the system deployed on a few repositories, and this is how a typical suggestion looks like. In this case, the developer is recommended to make suggestions or make change edits in sandbox pfx mappings.xml because they have edited some of the correlated files. In addition to this, we also provide a list of previous PRs where these files were changed together so as to provide more information about the correlation to the developers. We got the system deployed in about 50 repositories for 2 months, and we realized that even though REX was able to generate a lot of high impact suggestions that helped save misconfigurations, but there were many suggestions that the developers found irrelevant. And the reason, of course, was because change rule discovery is a coarse-grained approach and it does not take into account the actual diff content. What I mean here is, even if a developer goes ahead and adds a new line in file X, we would still end up recommending file Y, which is not going to be a relevant suggestion to the developer. So this motivated us to work on the second part of REX, which is change rule refinement. So once we have learned rules from change rule discovery, we need to put some filters to improve the precision or performance of model. So let me talk about change rule refinement. As part of change rule refinement, we wanted to understand what kind of change in X is triggering a change in file Y. So again, taking an example here of in file X, there was a version update that triggered a similar version update in file Y. But when there was a reference added in file X, there was no change in file Y. And so basically, this means that file X and Y are correlated for version updates, but not on addition of references. And each such correlation was different for different file pairs. For every file pair, we wanted to understand what kind of change in X leads to a change in file Y. For this, we have built a pipeline where we take as input the changes in file X, cluster them based on their features, and then use an inductive generalization technique to learn the most specific generalization of the changes in file X that triggered a change in file Y. Now let me talk about the inductive generalization part first. So taking an example, let's say file X was changed in 3 commits, and this is how the change looks like. So file X is an XML file and the change was made in command config node with a network node. Now if I have to generalize these 3 changes, one generalization could look like this, where I say that file X was changed and I do not really care about what was changed in file X. This is nothing but change rule discovery model. The second generalization could look like this, where I say that something was changed in network node, but I really do not care what was changed in network node. But what I'm interested to know is this kind of more specific generalization where it clearly specifies that the change was made in command config node with a network node. This is the more specific generalization, and we use a technique called anti-unification to learn this. We decided to use this technique is because based on analysis, we realized that a lot of config files have some sort of structure associated with them, and anti-unification helps us to exploit that structure very well. So as part of anti-unification, the first step is to generate the diff data. Now again, taking back the previous example, this was commit 1 where file X was changed, and if we look at this commit and extract the text diff out of it, this is how the text diff looks like. Similarly, for other commits, the text diff looks like this. Now if I just concentrate on the right hand side of the slide and just look at text diffs, basically, and apply generalization on top of it, I'm going to learn nothing because there's nothing common in the text diffs. But if I expand the context around the text diff and take into account the node or the attribute which was changed, I can learn a much more meaningful generalization which looks like this. So for all the changes that were made, we do context expansion around the diff as part of our data set for anti-unification. Once we have the context expanded diff data, the second step is to generate a tree. So what we do is, so again taking back the previous example, this is what the context expanded diff looks like. Now this is the corresponding tree for this context expanded diff. The root node is network. It has two child nodes of type attribute, and the third node is type command config. The differences in the value of attribute are highlighted with different colors. So similarly for other two commits, this is how the tree looks like. Once we have these trees, then we run a set of two rules as part of anti-unification to extract the common subtree out of it and replace the differences with asterisks or holes. So this is how the common subtree looks like. Converting the common subtree back into node, this is the XML node or the most specific generalization of the changes that were made in file X. So this covers the inductive generalization part. Now let me talk about the importance of clustering. So again, taking back the previous case where 3 commits were made for file X and the change was made in network node. Now what if there's another scenario where in addition to 3 commits, there were 2 more commits, but this time the change was made in cert group node and not network node. So before doing inductive generalization, we divide these changes into 2 clusters. Why this is important is because let's say if I do not divide them into 2 clusters and randomly pick 2 nodes to start anti-unification, I end up learning nothing because there's nothing common between network node and cert group node. If I divide them into different clusters based on the node name and attribute types, then somewhere in the hierarchy of these clusters, we learn more specific generalizations for individual cluster, and this is what we are interested in. Once we have learned the more specific generalizations for individual clusters, we use them to enhance our rules. So for every rule that we have learned from change rule discovery part, we add these generalizations that we have learned from change rule refinement part to enhance the rules. Now we make a suggestion for file Y only if the change made in file X matches any of these generalizations. So let me briefly talk about the deployment of Rex. So we got the first version of Rex deployed in about June 18, and within 2 years we basically scaled it out and deployed the second version of Rex, which was the change rule refinement part. Currently, it is deployed on 360 repositories. It processes more than 1000k pull request updates per day, and it has made more than 5000 recommendations which developers have found useful and they acted upon. But then the question arises, how do we evaluate such a system called Rex? So again, talking about evaluation metrics, let me take an example. Let's say a model detects 100 correlations, out of which 80 are true positive and 20 are false positives. So the model precision will be 80%. But in a real world, developers are not going to forget all the 80 correlations. On an average, they would miss about 5 to 10%. They would still remember making changes in 72 of the suggestions that were made by this model. But when we get the system deployed Rex, we're not going to make recommendations for the correlations that the developers have already remembered to make edit for. So we will recommend only 8 missed true positive cases and 20 false positive cases. So the deployment precision for Rex would look like 8 by 28, which is much lower than 80%. So even though the deployment precision is much lower, but each such true positive that is flagged by Rex actually helps developer save a lot of time and and companies save millions of dollars. So we have selected about 6 repositories within Microsoft and evaluated Rex on it. So the second and third column talks about model precision with and without change rule refinement, and the last 2 columns talk about deployment precision with and without change rule refinement. As you can see, with change rule refinement, both model precision and deployment precision have significantly improved on values without change rule refinement. On an average, we are able to achieve about 20% of deployment precision across different Microsoft repositories. In addition to this quantitative analysis, we did a qualitative analysis where we sent email to about 328 engineers working across 5 different teams, and this user study was conducted in 3 phases. So even though our deployment precision was low, about 20 to 25%, we found that about 63.4 users found the suggestions very relevant, and the reason they were not able to act upon it were various was something that was not related to the model. They had time constraints, or they were making changes in a separate PR which our evaluation system is not able to capture. Additionally, 43.8 suggestions were high impact suggestions that actually helped save service disruptions or build failures. So these are some of the anecdotes that we got from different users. So as part of future work, of course, there's a scope of improvement, and we are planning to use a combined approach of program synthesis and machine learning to come up with a holistic method towards configuration management. In addition to this, we're also planning to scale out regs to 100,000 repositories within Microsoft, and this is actually under process right now. So I would like to summarize today's talk. So as I said, failures due to misconfigurations have become a critical problem, and we have developed Rex, a correlated change analysis tool to detect these misconfigurations. Rex exploits historical commit data to learn change rules, and it has been deployed in 360 repositories within Microsoft for about 2 years. Till date, it has made about 5,000 recommendations which developers have found relevant, and they have acted upon it. So thank you, and I'll open it up for questions. In case I'm not able to answer it today, you feel free to email it to me. Thank you.